So far, we've been considering the effects of the magnetic field on single charge particles that are moving through the magnetic field. Let's consider a case where we have an electric current which goes through a wire. So here's a piece of a wire of length L, and it's in a magnetic field. The field is pointing up. And a current is, of course, made up of charged particles that are moving. So the moving charged particles, those are the conduction electrons. They're moving along this conducting wire. Well, they're going to feel a force, okay, because they're charged particles moving in a magnetic field. Let's see. We have a picture over here. We have the wire. We have the positively charged atoms. Okay, atoms have protons and electrons as well as neutrons. Some of the electrons are stripped off the atoms. Those are the conduction electrons. So leaving a positively charged atom behind. Those do not move. Those are fixed. It's the negative conduction electrons, these ones here, that are moving in what direction? Well, if the current is moving to the right, the convention is that means the negative electrons are moving to the left. Okay, so it's backwards from what you might guess when it's negative charges moving in a current. Anyway, again, the basic idea is we have a current, charges moving, moving charges are associated with that current. If it's in a magnetic field, there will be a force. And in this case, when the current is moving to the right, again, that will actually mean physically the negative charged particles are moving to the left. There will be a force pulling on those charged particles, and it will be pulling upwards. Okay, so the magnetic force on the electrons will be pulling them up, and the effect of that is going to be, well, these electrons cannot get outside of that metal, so they pull the whole metal wire up, and as a result, there's a force upwards on that wire that's carrying the current. Okay, so that's the basic idea. Here's, again, our equation that we have been working with, this one here. F is Q, V cross B. Now, you can do a little bit of manipulation. I won't do the derivation in these notes. I think you can probably find that in the textbook. But you can show that this equation ultimately leads to equation 3. And what is equation 3? It's telling you the force on a piece of wire of length L carrying a current I moving through a magnetic field. In the original equation, we had V cross B. Now we have L, vector L cross B. What is the vector L? Well, the scalar L is just the length of the wire, but we make a vector out of it just by choosing a direction to be the direction of the current. So here you see the current is going a little bit upwards and to the right. So the vector L will be pointing from that point to that point. And that's the vector you need to calculate this cross product. So L cross B multiplied by the current, that will give you the magnetic force acting on the wire. Okay, so if you do a little, see, I can't show both things on this screen at the same time, but if you look at equation 3, so look at equation 3 in your notes or write it down, and then look at this problem over here, and what do we have? We have a magnetic field. The dots mean the magnetic field lines are coming out of the plane of the screen. And let's say there's a current going through this wire. It's a piece of a wire. And we find the wire bows a little bit when current goes through it. And it bows upwards. That just indicates the wire is being pulled upwards. So the question is, obviously it's feeling a force that's causing it to bow, and this force is pointing upwards. The force requires that there be a current going through this wire. What direction is the current going? Okay, let's make a guess. Let's say it's moving to the right. Okay, if it's moving to the right, current is moving to the right, go back to this equation. F is IL cross B. If it's moving to the right, then the vector L is in the direction of the current I. pointing to the right. Take the cross product with the magnetic field. Okay, so do this right-hand rule for the cross product. So take your right hand, point the fingers of your right hand to the right. Okay, and then you want to curl your fingers in the direction of the magnetic field, which is coming out of the screen. And I think if you want to do this, you have to turn your hand so that your thumb is pointing down. Then you can curl your fingers in the direction of the magnetic field. Well, down is not the direction of the force. The force is actually pulling the wire upwards. So we guessed wrong. So let's try again. Let's say that the current is going from right to left. If it's going from right to left, point the fingers of your right hand to the left, and then curl the fingers of your right hand, don't forget it's your right hand, in the direction of the magnetic field. Well, you're probably going to have to turn your hand so your thumb is now pointing upwards. Then your fingers can come out of the plane of the screen. And thumb pointing up means that's the direction of the force predicted. If the current goes from the right to the left, that's consistent with what's in the picture. So that's the direction that the current is flowing. Okay, you may need to think about that and practice that a few times, but it's important to understand how to use the right-hand rule to calculate directions of vectors that come out of cross products. Okay, what else can we say? So far, we've been looking at what the effects of a magnetic field are on the motion of charged particles, whether they're individual point charges like electrons, or whether they're currents flowing through electrical wires. That was the very last thing we looked at. What we've not said anything about yet is what is the origin of a magnetic field. Okay, so here is a famous experiment that was done about 200 years ago. So this is a wire, and the wire initially has no electric current in it. Okay, and then you have this plane, this square, just like a little table, which is attached to the wire. And on that table you put a collection of compass needles. So these are the old-fashioned compasses that point towards the magnetic north. Because the Earth has a magnetic field, these compass needles will tend to line up with the Earth's magnetic field and point towards the magnetic north. The magnetic north is close to, but not exactly at, the actual north pole of the Earth. So it doesn't point perfectly north, but it points roughly in that direction. Well, that's what happens if there's no current going through this wire. But if you pass a current through the wire, something happens. These compass needles forget all about the Earth's magnetic field, and they will tend to line up in a completely different way. In fact, you'll see this kind of circular pattern of the orientations of the compass needles. And what that's indicating is that there is a magnetic field which is created by this wire carrying this current, and the magnetic field is described by field lines which form circles around the wire, perpendicular to the wire, the plane perpendicular to the wire, as you see here. Okay, what's the direction of the magnetic field? Okay, well, magnetic field will be pointing tangent at any given point on one of the points on the magnetic field line, this circle. But does it point clockwise or counterclockwise? Well, the rule is given here. It's another right-hand rule, and this one's a little bit easier. You take your right hand, not your left, take your right hand, and you point your thumb in the direction of the current, and your fingers curl in the direction of the magnetic field. That turns out to be the correct direction of the magnetic field. Okay? So What this tells us is the thing that is causing a magnetic field to exist is the presence of an electric current. Or in other words, moving charges create magnetic fields. Now that's not the only cause of magnetism. In fact, the magnetism you're most familiar with, bar magnets, pieces of magnetized iron, fridge magnets that you stick on your fridge, it's a little bit more subtle in that case, but it's something like this, okay? It's not actually electric current that's flowing, it's a little bit different. Don't worry about that kind of magnetism. For this course, we only care about the kind of magnetism that's created by electric currents like this. Okay, so it turns out that for a very long straight wire, the magnetic field lines are concentric circles. Okay, we've already said the magnetic field lines are circles. Well, here's one of the magnetic field lines, here's another one, and here's another one. And they're all these circles are perpendicular to the current carrying wire. And it turns out that the magnitude of the magnetic field is proportional to the current I. And we have a constant here, mu naught, 4 pi times 10 to the minus 7. And this is called the magnetic permeability of free space. You don't need to remember that, but all you need to know is it is one of the constants of nature. And the magnetic field is also inversely proportional to the distance r away from the wire. Okay, so for these magnetic field lines, which are circles, r would also be the radius of the circle. Okay, so the important thing to remember is for a long straight wire, this is the expression for the magnitude of the magnetic field. The direction of the magnetic field is given by the shapes of these magnetic field lines. Okay, so you take a point on one of these lines, tangent to that circle in the direction of the arrow. That's the direction of the magnetic field at that point. Just like was the case when we talked about electric field lines. Same idea. Okay, and the direction of the magnetic field is determined, of course, by the magnetic field lines, like I just said, but the right-hand rule will tell you whether these field lines are going clockwise or counterclockwise, which direction they go in. Okay, and what else? Oh, and the magnetic field decreases, not surprisingly, the magnetic field decreases as the distance r increases. The further away you get from the wire is the source of the magnetic field. The further away you get from the source, the weaker the magnetic field is. Okay, so there's what we can say about the origin of a magnetic field. So let's say that you have two current-carrying wires here. And we know a couple things now. We know that the magnetic field caused by a current-carrying wire, a distance r away, is mu naught I divided by 2 pi r. And we also know that if you have a current-carrying wire in a magnetic field, that it will feel a force. So I know this is kind of a confusing picture here, but here's the basic idea. Here's current I1, so the lower wire here, and here's I2, the upper one. So at a point along wire number 2, there is a magnetic field caused by current I1. Okay, so the circles that go around current I1, okay, that's the magnetic field. The magnetic field lines associated with current I1. Well, one of these lines just happens to intersect current I2, and the magnetic field caused by wire 1 at the site of a point on wire 2 is B1.